Module 1, Lesson 2, Bisection Method. For this module, we will then discuss the different types of nonlinear functions, the different bracketing techniques, one of the bracketing techniques called bisection method, the bracketing condition, the derivation of its iterative formula, and a sample problem involving bisection method. What are the different types of nonlinear equations? The first type of nonlinear equation is known as the algebraic equation or polynomial equation, given in the standard form of a multiplied by x raised to an n power, where your an refers to your constant coefficient and your x is raised to a certain degree of your polynomial, which is often given as a positive integer. Note that when dealing with nonlinear polynomial functions, the roots of your nonlinear polynomial functions depend on your integer value n. The roots will either be a real number or a complex conjugate. The other type of nonlinear equation is called the transcendental equation, which may come in the form of a trigonometric equation, an exponential equation, a logarithmic equation, or a natural logarithm equation. This particular type of equation is not given in a polynomial form, and there can be infinite number of roots on a given particular transcendental function, or a finite number of roots, or in some cases no roots at all. One of the more practical way of solving both polynomial and transcendental function is by the use of an iterative method. It involves iterations in such a way that the computed values of x are convergent. The values of x are said to be convergent if they are approaching the actual root value. Otherwise, it is divergent. If the given equation has the form wherein f of x is a nonlinear function, then an iterative equation from the form can be acquired, as well as the iterative formula of the form. This technique is very efficient in solving the roots for both nonlinear polynomial function and nonlinear transcendental function. The iterative method often contains two major components. The first one is the iterative or recursive formula and a terminating condition. The terminating condition states when to stop applying the iterative formula. It may be based from the following. One, if by chance the computed value after applying the iterative formula for the first time turns out to be the actual root, then the process eventually is terminated. Number two, if a specified number of iterations is often given in the problem. However, in this particular case, sometimes the corresponding root still has not been reached through the specified number of iterations. Now, number three, which is the most common and the one applied in most iterative techniques, if the given error criterion in the problem is satisfied, that is by using the precision type error criteria that we have discussed on the previous module, like the absolute error criteria or the relative error criteria. These particular techniques that are referred to as bracketing techniques makes use of two initial guesses which eventually bracket your respective root. The particular method described herein employs different strategies to systematically reduce the width of your bracket and hence home in on the correct answer, or basically converge in to your correct root. The first technique involving your bracketing technique is known as the interhalving method or bisection method. This bisection method, which is also known as a binary search or interhalving method, is an ancient and most elementary technique, but very effective method for finding the roots of your corresponding function. This method is applicable for both polynomial and transcendental function. This technique sets up two initial values, which are referred to as x0 and x1. And the corresponding functions for each respective values of initial integer values of x must have opposite signs of function. due to the fact that it should satisfy the bracketing condition. As seen on this bracketing condition, if you multiply the corresponding function fx0 and fx1 generated by your initial integer values x0 and x1, the product must always be less than 0. And that will only occur if your functions fx0 and fx1 are in opposite sign. This is the corresponding graphical depiction of the technique and how it works. You first set up two initial values on your corresponding estimate. x0 bearing the negative function, x1 here bearing the positive function. And then you then treat the distance between x0 and x1 as a line segment and subdivide it by 2, giving you your root estimate x2. The process then verifies if x2 is your root by checking if fx2 is 0. If fx2 is not 0, then we simply replace one of these bracket values. In this case, I replace x1, since fx2 is positive, and then replace your x2 with x1, and then repeat the process again for the segment x0 to x1. The iterative formula then for this given technique is a midpoint formula, which is given off by either this corresponding formula or this formula. After solving the root estimate x2, we then substitute x2 to your function in order to obtain fx2. If fx2 is not equal to 0, then we will replace one of its bracket values. If fx2 turns out to be greater than 0, then we replace the positive function limit value of x with x2. But if fx2 turns out to be less than 0, then we will replace the negative function limit value of x with x2. And then the process is repeated until the terminating condition is satisfied. The terminating condition for the given technique is often based from your precision type error, which is either by using an absolute error criteria or a relative error criteria. Let's try to evaluate then and apply that on this given example. We're asked to evaluate the root of this given particular function using bisection method. So the first process is to equate your given function to 0, regardless whether your function is polynomial or transcendental, and then set up possible initial values for your corresponding limits, x0 and x1, by tabulating integer values. If you tabulate then initial integer values by substituting different values of x to your function, you'd end up with the following function values. And you will notice that on this given particular integer values, you have satisfied that particular condition. This integer initial value gives you a negative function, while this initial integer value gives you a positive function. I have selected, of course, the initial integer values that are close to your respective root position. You may also select any integer value that yields negative function and an integer value that leads a positive function. The first iteration then would appear like this. I have set up my initial integer values 4 and 5 with my corresponding functions -6 and +20, thereby satisfying my bracketing condition, and then obtain its midpoint, which is now equivalent to 4.5. After which I substitute your corresponding fx2 to your given x2 to your given function, giving us a value of 4.625. Note that this particular function value is not 0. So we then replace one of the bracket values of your x. In which case, since our given fx2 turns out to be positive, I will then replace this positive function limit value of x, which is x1, with x2. Hence, on the next iteration, my x0 remains 4, while my x1 remains 4.5. Note that this initial value still satisfies your bracketing condition, which implies that your root value is still between 4 and 4.5. We then continue on by solving for its midpoint, ending up with a value of 4.25, and substituting that to your function gives us this corresponding function value fx2, which is negative 1.2344. Afterwards, we solve for the absolute error, which is the criteria, by comparing our two calculated values of x2, which is the new calculated value and your previous computed value, giving us an absolute difference of 0.25. This absolute error obviously do not satisfy our terminating condition. So we then replace one of the bracket values again. And as it turns out, this respective fx2 is negative. Therefore, I will replace negative function limit value of x, which is x0, with x2. So on the next iteration, I then set up these values, x0 and x1. And note that these values of x0 and x1 still satisfies my bracketing condition. I then repeat the process by solving for its midpoint, ending up with a value of 4.375, and substituting that to our function gives us a value of 1.5527. Obtaining the absolute error now, obviously I need to repeat the process by replacing x1 with x2. Thus, on the fourth iteration, this now would be my given values for x0 and x1. I evaluate its midpoint, which is 4.3125, and substitute that to our function, giving us a function fx2 value of 0.1243. Solving for the absolute error, we've seen that we need to repeat the process and again replace x1 with x2. Thus, on the fifth iteration, this would be our given values for x0 and x1. We then evaluate its midpoint, which is now 4.2813, and substituting that to our function gives us a function value of negative 0.5626. Obtaining the absolute error now, obviously it shows us that we need to replace x0 with x1 and repeat the process again. Thus, on our sixth iteration, this would be our given value. Hence, we evaluate its midpoint, ending up with a value of 4.2969. And substituting that to your given function gives you a negative value of 0.2213. Evaluating its error, it shows us that we need to repeat the process. Hence, we replace x0 with x2 again. So on the seventh iteration, this now would be our given values. Your midpoint now would be 4.3047. Substituting that to our function gives us negative 0.0491. Obtaining the absolute error criteria gives us a value of 0.0078, which implies that we need to repeat the process, replacing x0 with x2. So on the eighth iteration, this would be our given values now. Solving for its midpoint, you have 4.3086. Evaluating your function fx2 gives us 0.0375. Obtaining the absolute error eventually shows us that we still need to continue the process. Thus, we replace x1 with x2. On the ninth iteration, then, this would be our given values. Solving for its midpoint would now give us 4.3067. Substituting this to your function gives us a value of negative 0.0047. And obtaining the absolute error, it eventually shows us that, again, we need to repeat the process. Hence, we replace x0 with x2. So on the 10th iteration, this now would be our given values. Solving for its midpoint gives us 4.3077. Substituting that to your function gives us a function value of 0.0175. And obtaining the error gives us a value of 0.001, which eventually indicates that we need to replace x1 with x2. Hence, on the 11th iteration, we now have this given values, and its midpoint would be 4.3072. Substituting that to our function gives us a function value of 0.0064 and an absolute error of 0.0005. Hence, again, we repeat the process by replacing x1 with x2. So on our 12th iteration, we end up with this given values and this midpoint to be 4.3070. Substituting that to your function gives us a function value of 0.0019 and an absolute error difference equal to 0.0002. which means that we need to continue on again the process, replacing x1 with x2. And on the 13th iteration, we end up with this given values for your x0 and x1 and a midpoint of 4.3069. Substituting that to our function gives us a function value of negative 0.0003. And if you then evaluate for the error criteria, you would notice that it's now 0.0001, which satisfies your terminating condition. Thus, we now stop the iteration, ending up with a final value for your root that eventually converges to 4.3069. If we then summarize your tabulated solution, you'd end up with this respective table of values, starting from the first iteration down to your 13th iteration, showing you the different corresponding function values fx2 and your respective midpoint value, ending up with a value of 4.3069. This ends the module.